Hello and welcome to the WIDS Upskill Workshop Series for 2024. Two instructors today. So we have Millicent Ochieng and Diana Muthe EU. So Millicent is a seasoned data and applied scientist currently spearheading significant research initiatives at the Microsoft Africa Research Institute in Nairobi, Kenya, with an acute focus on multilingual natural language processing and developing AI solutions for low source languages. She is a proud recipient of the IUCA Master's Scholarship Award. Millicent completed her Master's of Science in Data Science at the University of Rwanda, where she explored transfer learning techniques for precision agriculture under the mentorship of Dr. Pan of Harvard University and Dr. Fernandez of Microsoft Research. As an ardent advocate for gender equality and representation in STEM fields, she continually seeks opportunities to foster inclusivity and innovation in the industry. Millicent's commitment to excellence and passion for bridging the technological divide with AI advancements are evident in her contributions as a woman in data science ambassador for both Africa and Kenya. So thank you so much, Millicent, for all of your contributions. I'm going to read Diana's bio next. So Diana is an associate data scientist at Roche. As an associate, she supports a postdoctorate data scientist in a project to predict cardiac adverse events using machine learning algorithms and electronic health records data. Before this, Diana worked with healthcare startups on AI projects to find a correlation between symptoms, triggers, and morbidity for Hashimoto's disease, and another building predictive models using EMG signals and patient data to detect and predict painful behaviors for lateral elbow patients. She is also an instructor at Code First Girls UK, where she gets to teach and guide other women into a career in data science. Diana enjoys organizing events and workshops related to tech, AI, and data science, and also volunteers as a Google Women Tech Maker Ambassador and Women in Data Science Kenya community organizer. She's currently at the onset of her Master's of Science in Big Data Analytics at the University of Liverpool and looks forward to publishing papers on research in healthcare and AI. Thank you for your contributions, Diana, as well. Without further delay, we have the following workshop from Millicent and Diana, Empowering Healthcare with Machine Learning, a hands-on approach. They will take questions at the end, but please feel free to put your questions in the Q&A section throughout. Thank you so much, and let's give a warm welcome to Millicent and Diana.
Good morning, good afternoon, evening, everyone, and thank you very, very much for joining us today. We are excited that you are here. My name is Millicent Ochieng, like Lovera has mentioned, and I will be doing this presentation along with Diana Muthe. Today, we will be diving into our presentation titled Empowering Healthcare with Machine Learning approach, and our goal is to explore how machine learning is a transformative force in the field of healthcare. So we've designed this session to be very, very beginner friendly and much insightful. And we are sorry if you will be familiar with very many of the concepts, but we really wanted to make it beginner friendly. We've combined key concepts with practical applications. So whether you are new to machine learning or looking to see its impact in healthcare, this session is definitely for you. So please meet Millicent and Diana. I mean, Lovera just gave us a wonderful introduction, and there is no need. This is us. Cool. So let's start with an overview of today's session. So we've structured our presentation into 5 key sections. First, we'll give an introduction of overview of machine learning to set the stage for understanding its basic principles. Next, we'll dive deeper into the fundamentals of machine learning, where we'll explore core concepts and types of machine learning. Next, in real-world applications of machine learning, we will showcase how these concepts are transforming healthcare. And then in our hands-on experience, hands-on tutorial, which is the session that Diana will take over, will then give you a practical experience of applying machine learning in the field of healthcare. And then we'll wrap up, as Lovera mentioned, with a Q&A session where we look forward actually to answering your questions and a lively discussion. So welcome to the presentation. So let's begin by defining machine learning. So at its core, this is a technique that allows computers to actually learn and make decisions from data without being explicitly programmed from every scenario, right? So this capability actually provides a foundation for computers to uncover insights, recognize patterns, and make predictions, which is especially transformative in various fields, for instance, like agriculture, and healthcare, which is our field of interest today. I mean, think of machine learning as teaching computers to think and basically analyze data like human experts, but at scale and at a speed that is actually not possible to be done manually. So in healthcare, machine learning takes on a specific and very, very crucial role, right? It involves applying machine learning algorithms to enhance various aspects of patient care. So if I mention stuff like algorithm, please just hold on because I'm going to explain what that is. So this includes improving patients' outcomes, more accurate diagnosis and personalized treatments, reducing healthcare costs by optimizing resources and elevating the overall quality of care. And the end goal is basically to leverage this technology not just for efficiency, but for, to fundamentally improve how healthcare services are delivered and experienced by patients. So healthcare is an incredible data intensive, right? Vast amounts of data are generated in healthcare, right? Like patients' records, right? Medical imaging, clinical trials, and so forth. This data, when analyzed effectively, it can lead to significant improvements in patient outcomes, cost reduction, and overall enhancement of healthcare services. So machine learning excels in this extracting insights from these complex and large data sets, making it a powerful tool in transforming healthcare data into actionable knowledge. So the role of machine learning in healthcare is actually to empower medical providers or professionals in the field to make sense out of the data that they generate. By analyzing data quickly and accurately, machine learning algorithms can actually identify patterns, trends, and make predictions. So this analytical power translates into more effective healthcare delivery, leading to better diagnosis or detection of diseases, more personalized treatments, plans tailored to actually individuals' patient needs, and basically the overall enhancing the overall healthcare services. So essentially, machine learning acts as this sophisticated or data-driven assistant, enhancing the decision-making process in this particular space. So having looked at the impactful role of machine learning in healthcare, let's turn our focus to the fundamentals of machine learning itself, because understanding the basics is crucial for grasping how these technologies are applied in the field of healthcare. So we'll start by defining the model algorithm that I was mentioning previously. So at the heart of machine learning is the concept of a model, a machine learning model. So when we talk about machine learning, what do we actually mean, right? So a machine learning model extracts patterns from data, right? If data given to the model is labeled, and the task is actually to predict labels for new labels, then this is a supervised learning problem. What do I mean? So you have a bunch of fruits. We have green apples. I mean, not just fruits, so many, like we have green apples, we have red apples. So by labeling them as red or green, this type of data is actually a labeled data, right? And if the task is to predict labels for some new label, now you give the machine an apple, right, which is red, and you are trying to ask it, like, what's the color, something like that. We call that a supervised learning problem. So in this case, or in this particular problem, we have two other problems, that is classification problem and regression problem. Now, if, for example, the example that I just gave, your task is to actually predict a label for a category, green or red apple, right? For example, in credit scoring, which is a task that machine learning has excelled in, classifying clients as either default or non-default, right? Those are categories. Data can either be in form of categories or in form of numerical. So when it is a category, when the problem is a category, involves a categorical label, then we call that a classification problem. Now, if the label is actually a real number, it's numerical. For example, predict the weight of an apple in kilograms or in grams, then we call that particular problem a regression problem, right? Aside from supervised machine learning problem, because in this space we have labels, so usually there are in a data we have the X, the covariates, so the predictors, and then Y, which is what I'm talking about, the labels. So in supervised learning, you have both the X's and your Y. So in unsupervised learning setting, you actually have pretty much, let me go back to my fruits example. You just have a bunch of red and blue, sorry, we have red apples and green apples, and perhaps grapes as well, right? Green and red. And so the task is to find groupings and structures within that particular data. We call that kind of problem unsupervised learning problem, because your task is not to give labels to, like, this is a grape, this is an apple. Your task is to just separate the green apples and grapes from red ones. Then that particular task is basically unsupervised learning problem. If you do have a question around that, please feel free to drop a question in the chat window. Because understanding these distinctions is actually crucial, as it informs how we approach different machine learning problems. Now, the different algorithms that I was talking about are here. We have different machine learning algorithms for supervised learning problems and unsupervised learning problems. So for the supervised learning problems, you can see a different other categorization called regression models or algorithms, and classification algorithms, right? Where we have for classification, all those different other algorithms. And these are not the only possible algorithms. We have lots and lots of different other that have been designed for us to, like, help us work around our machine learning problems. And so for supervised learning problems, learning algorithms, I mean, you see that I mean, they actually, so this particular task, they are actually important. These algorithms are actually important in tasks where the data is known labels, like I mentioned before. And for unsupervised learning case, where we have the K-means or the principal component analysis, we have, I mean, they are very, very crucial for us when we are dealing with data without actually predefined labels. And we just need to find patterns within the data. I'll now take you through different steps involved in building a machine learning model. One, we because machine learning model is powered by data. So data is the foundation, right? We collect the relevant data from various sources, such as electronic health records, medical devices, and research databases for our healthcare problem. And then after collecting and gathering relevant, okay, first of all, you must be having a problem that you want to solve, right? So for our hands-on, you will see that we will be solving a particular problem. And then for that problem, you will try to find relevant data. So here I started with get data, but actually the first step is what exactly is the problem that you're trying to solve. So given the problem, you have to get your data. And then it has to be very, very relevant to your project, to your problem. And then step two, you, in most cases in real world, you're not going to find a perfect data. So step two is going to involve cleaning and preparing and doing some data manipulation. And we're going to see all these in our hands-on, whereby data will need to be cleaned off of errors and to be formatted correctly. And we'll do some. You'll need to do some data transformation, what we call feature engineering. But I really don't want to dive so much into that because Dana will be talking about that as she is doing it practically. And then once you have all your data, you might want to divide it into a certain fraction, like either 70, 30, or whichever way you want. But mostly people use like a third of their data. They want to set that aside for testing purposes. So you'd want to use one chunk of your data for training your machine learning model. So you use that prepared data to train your machine learning model and allow it to learn the patterns from the data. So like we just said, it does nothing but just try to extract patterns within the data that you will have given it, right? From there, you just try and evaluate your model. You test your model using the data that you had set aside. And in some cases, we even try to test it with some other real-world data in the same field. But then let's talk about the data that you had set aside for your evaluation. You will be happy with your model or you will not be happy with your model. If you're happy, well and good, but this is usually a very iterative process. You go back to your model. You will not have like the best, if at all, accuracy you are using for your as your metrics or class, whichever the metrics that you'll be using, right? You'll want to improve the performance of your machine learning model. And so step 5 is to improve your model based on the model's performance. We iterate and enhance the model, changing things to improve its accuracy and effectiveness on the data that we want it to like in the problem that we will want it to solve for us. Sorry. So these steps are very, very iterative, often requiring multiple rounds to refine the model for the best results. For example, in healthcare applications, let's look at some of the real-world applications of machine learning in healthcare. So first, and these are not the only possible machine learning applications in healthcare. We have lots and lots of different applications. I just gathered this to give you like a glimpse of what exactly we can use machine learning for in healthcare. I mean, you will go and you will like find lots and lots of other applications in the same space. So in disease diagnosis and prediction, machine learning models, particularly neural networks, are increasingly being used in disease diagnosis, right? From medical images like X-rays, MRIs, CT scans, and they are actually performing with a high accuracy. And this has seen to be providing much assistance to medical practitioners in this field, like the radiologists. Predictive models are also being used to forecast patients' risks, such as predicting the likelihood of like heart attacks or strokes based on the patient's history and lifestyle factors. When we move to personalized treatment and medicine, so you find that by analyzing the patient's data, machine learning enables healthcare providers to create these customized treatment plans for different patients. And this has a profound impact on oncology, for instance, allowing for cancer treatments to be tailored to genetic makeup of individual tumors. In the realm of drug discovery and development, we've seen in the pharmaceutical industry, machine learning has accelerated drug discovery by analyzing complex. We've seen how machine learning can analyze complex and vast amount of data. So in this space, machine learning has accelerated drug discovery by analyzing complex biochemical data. It helps in identifying potential drug candidates like faster, I mean, compared to our traditional methods, right? So lastly, I was going to talk about remote patients monitoring and telehealth. So this one we've been observed like much more here in Kenya, where we have some healthcare centers are very far away from like where patients live, right? So in this space, machine learning is integrated with wearables technology to monitor patients' health in real time, which is particularly valuable for managing chronic conditions outside of like the clinic setup. So the one that I was talking about is like this space where maternal mothers have been equipped with these wearables, and then medical practitioners can actually monitor their health while they are like far away, and they are being reminded like this is your time to go for like your antenatal appointments and so forth and so on. So machine learning is actually transforming the field of healthcare, and this is exciting. So having explored this theory in application areas, I believe we have some foundation or understanding of how machine learning models are developed, the steps and so forth. So in this section, let's have an opportunity to apply what we've learned practically. So without further ado, we'll just hand it over to Diana to begin the hands-on session. So I just keep sharing for Diana to like talk about this problem that we designed for you in this. Then I'll just stop sharing for Diana to share her screen. Please take it away, Diana.
Okay. So okay, still waiting for you to stop sharing from your end.
Oh, okay. For some reasons, can you actually override me so that
No. Yeah.
Yeah.
Okay. Good. So we can get started with our notebook, and also keeping in mind that this year's challenge is a supervised machine learning challenge where you're supposed to predict whether or not a person got diagnosis within 90 days. Similarly, this will also be a supervised machine learning challenge, but with the diabetes care health data, not with breast cancer, the triple negative breast cancer as this year. So some of the algorithms that we use today will be similar to what you might apply into your datathon. The metrics to analyze your machine learning models will be similar to what we use today, because it is also today's session will also be a classification under the supervised machine learning aspect or method or section within the machine learning divisions that Millicent just mentioned. So keeping in mind that you will be rated against the ROC AUC method, that's the area under the curve method, which basically checks your true positive rate against your false positive rate. So this is what your models will be rated against for you to be awarded in terms of the awards, right? So rating the performance of your given model, but as long as you participate and make a number of submissions, I think you should be qualified to get your certification. So we'll look at a very common data set that might be common to many, right? So it is a data set collected by the Behavioral Risk Factor Surveillance System, where they basically sent out surveys to every year to over 400K Americans on health-related risk behaviors, chronic health conditions, and the use of preventive services. So we'll basically try and answer some of these questions. So can survey questions really provide accurate predictions of whether an individual has diabetes or not? Then what risk factors are most predictive of diabetes risk? Can we use a subset of risk factors to predict accurately whether a person or an individual has diabetes or not? And can we create a short form of questions based of now feature selection, probably to see if someone might have a higher risk of diabetes or not. So also please, this will be shared after this. So just pay attention, take notes, and then you can iterate over again the second time after the notebook is shared, therefore creating that ground of actually understanding what we do a bit better. So again, remember to tie this up with what the datathon looks like. If you've already seen the data and the different columns, which some of them might be similar to what we already have today. So first things first, the first cell is usually importation of your libraries. So some of these libraries, pandas, this enables us to work with our data frames, which is the format of our given data. Then Seaborn, basically for visualizations, similarly to Matplotlib. So Seaborn is built on top of Matplotlib, and Seaborn is kind of a bit more beautiful and has more beautiful visualizations. So we'll do some bit of EDA just to understand our variables and how they kind of play along. So we also do have some pre-processing items that you can download, not download or import. We also do have some metrics that we'll try and use. Your confusion matrix, for example, the accuracy score, your classification report, for example, F1 score, the ROC AUC. I did not plot this because I kind of want to leave it onto you to go read and study about it, because this is what your model in the datathon will be rated against. So first things first is importation of your data set. That's the usual drill. We store it in a variable called df, put on there. So that's our data set up there. Then you'll realize that I've already loaded out just to save on time. Then the next thing we do is we do the .info, which is a function that lives within pandas, right? So it's used to check the general information about your data frame. because this is where we stored our data. So if we do the .info, we get some basic information about how our data set looks like. We can see the number of entries, the indexing of our data sets. So indexing in programming starts from 0. So 0 to this figure right here. Then this is our given column. So 0 to 21. So that means we have 22 columns. You get to see the non-null types. So this means that they don't have any null values to them. Definitely when you get data sets out there, if it's not data mined, it will be pretty clean. And then the data type that you do have, so you have your float in this case. Then first things first, we're going to try and see the spread or the distribution of our data set column, the prediction column that we're trying to predict, and that's the diabetes and binary. So with the Datathon data set, our column, the column you're trying to predict is already set up for you in 0 and 1, where someone got diagnosis after screening within 90 days, yes or no. That's the representation of 0 and 1. So do you have diabetes, yes or no? And this is what we have. So the non-diabetic are way more, and then the diabetic column is much, much less. So we can see that our data set or our predictive column is already imbalanced from the word go. So let's try and see characteristics of people with or without diabetes, which will help us shape our data and selecting some of the best features. So we start by looking at gender. So looking at gender, the distribution of gender between people who have diabetes. So those who have diabetes, that's equals to 1. Those without diabetes, that's equals to 0. So dot gender, which is our column, then you do the value counts, then multiply by 100 to get the percentage. We see that the gender 0 has 52, and then the gender 1 has 47%. So that's kind of the distribution when it comes to the diabetes, people with diabetes. So without diabetes or non-diabetic people, so our gender 0, which is female male, will be 56%, and then 43%. So we can already see the inclination between gender. So which gender tends to have more people with diabetes, and which one tends to have more people without diabetes, based off this item that we have right here, or statistics or EDA that we have. Then also looking at the education variable, which I think this was one pretty interesting aspect. So when you look at your given variable, that's the education. So with our Datathon, we have 82 variables. Here we have just 22 to work with. So the education variable, just to analyze it and see how it pans across. So we can see when it's 1, if a person selected 1, then they never attended school or only kindergarten, and so on up to 6. So if it's 6, that means college 4 years or more, or this person is basically a college graduate. If it's 5, some college training or technical school training. So getting to see in terms of 1, so 1, remember this is someone who's diabetic. We can see that quite a number of people reached, so we only have a range of those who have diabetic having education levels from 1 to 4, whereas people who do not have diabetes, quite a number of them are within the area of 6, right? So that even distribution, that distribution ranges from 1 to 6, and like the aspect of this where we do have 4 being the highest, and then this one 6 being the highest with 44%. So this actually, I found it a bit more interesting. Is it maybe because maybe by this time quite a number of people still do not know about nutritional aspect, or what relationship does this really have with a person having diabetes or not. So those are some of the questions that you do get to ask yourself when performing exploratory data analysis to understand the given columns better and how they interact with the predictive column, or the column that you are supposed to be predicting, or the dependent variable. So age distribution, again, let's try and see when it comes to 1, how does this distribute in that case? So when a person does not have diabetes, right? Or if a person has diabetes, let's try and see the distribution. And we can see a significant high between this area. So from the age of 45 to about 69, we have a significant increase, and the topmost being at the range of 65 to 69. So when it comes to the age column, it is advisable or better you bin up your age column just to get more insights instead of analyzing age by age. But this has already been done for you when it comes to the Datathon data set, where you already have your age kind of summed out, the 20s, the 30s, the 40s. So it will be a bit better to get information on that. So that's the distribution when it comes to, or the trend when it comes to someone who has diabetes. And then the age, so when you do the percentage over the age of people with the age of greater than 35, over 93% of all diabetic patients have a greater than or have an age equal or greater than 45. So from this age greater onwards, 93% of that are found to have diabetes. And then now looking at the distribution with a person without diabetes, we get to see this is it. So 83% compared to what we had for 93%. That is again being greater than that given age. So if we look at this, we can see that the sum or the count is a bit less when it comes to people with diabetes in the given age distributions, right? So it's there's a higher number when it comes to someone having diabetes within this given ages compared to not having diabetes in that aspect. So again, the notebook will be shared after this. Then the high blood pressure column, just trying to get that distribution or understanding of how this varies across someone who has diabetes and those who do not have. So if you have high blood pressure, that's what we represent by 1. Then having high blood pressure is 75%. Having 75% of those who have high blood pressure have diabetes. Then those who do not, that's 24% who have diabetes. Then if you do not have diabetes, then 62% of them do not also have high blood pressure. And then if you have high blood pressure, just 37% of them do not actually have diabetes, compared to 75% of them having diabetes if you also have high blood pressure. So this makes it very high at 75% to have diabetic and to be diabetic and also have high blood pressure. So you kind of see normally even what you had or read about, kind of the data also proves this to kind of be true. So also moving on to the high cholesterol being equal to 1, we see that the 6% is that you have high cholesterol and diabetes, then 3 of this percent of this have 32, should actually be 32. I just realized this should be a 0. I'll change this before that. So 67 and 32% against high cholesterol and having diabetes in that aspect. Then similarly to not having diabetes, so you do have 61% for that case, and then 38% if you do not, if you have high cholesterol levels. So high cholesterol levels are common in diabetic patients and much more lower in non-diabetic patients. So then they're having a heart disease or heart attack, chances of, if you've had a heart attack or heart disease before, how does this relate to diabetes or having diabetic or non-diabetic? So we see that this is 77%, 22% to have both diabetes and heart disease. So that's a bit lower and having node and 22% to have both diseases, so being heart disease or diabetic. And similarly to this, so for the diabetes binary, if you have no diabetes, chances are you also do not, we find that 92% do not have cholesterol and 7% do have that aspect of not having of having cholesterol. So patients with diabetes are 3 times more likely to have suffered a heart attack or gotten a given heart disease. You can check similarly to how stroke also relates to this, just to analyze just that's the concept or aspect of how you could perform your EDA to just see how this pans out, which is similarly to how we've done to the other columns. Then when it comes to BMI, what you do is also categorize this based on the rate that BMI is. We do have a column on BMI within our data set. So underweight, we have the ranges within the age against your weight. So we have the underweight, the normal, the overweight, the obesity, and morbid obesity. How this pans out or ranges out, and you get to see the distribution of those who have diabetes, how they spread across BMI level. Similarly, also doing this to those who have no diabetes or non-diabetic patients, see how this pans across for patients without diabetes, just to kind of see the tally and total between the range of the BMI and how this gets to pan out. So that's kind of how you perform EDA and get to understand deeper. If you find any meaningful insights, then you get deeper into that. This will be able to tell you if something is up with a certain column or how it relates to your given predictive aspect. So I'll just move on to, because this is also similarly to just getting to see how this actually relates to the BMI after we found some information, but this is the most important plot just to understand the underweight, how this performs when it comes to having no diabetes. And you can see obesity being quite high and high numbers when it comes to those who have diabetes, because again, diabetes and your nutrition really go hand in hand quite a lot. So you can get further into some more analytics that I have put on here and some of the items that I've put. So skipped some 4 cells that just get deeper into how age and BMI performs. Then another important aspect that can straight on tell you how they relate with the predictive column is plotting your correlation. By default, it's the Pearson correlation. So 0.5 and above, that's positively that's a high positive correlation, or you do put a threshold depending on what you're looking into or the certain disease. Sometimes 0.8 is what will be determined, sometimes points that in terms of positivity. And we also do have the negative correlations. So if it's a negative correlation, this means these two variables are negative to each other, right? So an increase in one item leads to a decrease in the other. But if it's positively correlated, so as we've seen, so high chances of getting, if you have high blood pressure, then you have high chances of having diabetes. So you'll find that positive correlation being on there. But we see that fruits and vegetables, for example, some of those that we didn't get deeper into, and then maybe if you have stroke, for example, the correlation is a bit lower in that aspect. So plotting this correlation just to see how this would look like in a visualization to tell us a bit better. The first variable is always positive to itself, so is always highly correlated to itself. That's diabetes healthcare. Then the diabetes column, then high blood pressure coming on next. Similarly to BMI, which we've just seen, and then general health. Do you have a proper general health? And your mental health, how this pans out to diabetes care. Then the ones that fall below this means that these have a negative correlation. So they might be high or low in terms of negative correlation aspect. So after you plot your correlation, you've performed your EDA, understood your given variables. Now it's time to actually prepare to build your machine learning model. And the first aspect is usually dropping irrelevant features. So based off this, if a column does not tell us a lot about the predictive or dependent variable, then we could drop them, because this will just be a lot of noise within our machine learning model or algorithm. So we drop against the axis of column, so axis 1. If it's 0, then that means you're dropping against the rows, which is not what you're looking for. We're looking to drop the column. So income, any health, fruits, vegetables, having pretty low correlation or not telling us much about that given dependent variable. Then the next thing, we do a copy of our data. Why do we do this? Because now we are moving into, this should have actually been done before the dropping, so that we just have that data set that we could go back to in case we need to go back to it. So the next thing we check, these are the columns that we have left. So the diabetes itself, high blood pressure, high cholesterol, BMI, smoke, stroke, heart disease, physical activities, heavy alcohol consumption, gender, age. So we've decided to keep all these aspects based on EDA or correlation, Pearson correlation that we have just plotted out. Then the next thing is we encode our categorical features. Why? Because the models I used did not digest your given or do not digest what do you call it, wordings, right? So human writing. So you have to convert this into numbers that will be digested by your given model. So this is something you have to do, especially with your basic or some of the classical machine learning algorithms, just to convert this into that zeros and ones or numbers, and that's called encoding. So your features that need to be encoded, label encoded, if you do have to have them encoded, then drop any duplicates if you do have duplicates, .sum. Drop any duplicates if you do have them as also part of your cleaning aspect, and then checking the dot value counts again. We see that the zeros and ones, this is what we are left with. We still have that imbalanced data aspect to that. So these duplicates that have been selected, we do drop them at this point. So dot drop duplicates, and this is what we are left with. So we have 168,510 compared to, I think it was 250 something initially. Then the value counts again to frame, just to understand the percentage of this. So that's basically 86% of non-diabetic and 13% of diabetic being on or placed on there. So we can use to do sampling methods, undersampling or oversampling, depending on what you do, depending on your data set and your understanding of the given methods, to increase or decrease one of these items, because it might need to a lot of bias, if I may put it in a simpler way. If you build a machine learning algorithm based off an imbalanced data set at this point, where this is way too huge, 86 against 13, that is a huge difference. So first things first, as you know, for your X variables, these are your independent variables. You need to drop off the diabetes binary against the axis, that's the column, and store each one of these separately. Then you do an oversampling, a random oversampling technique to have this event out before you actually build your given model. So you sample up this Y given on here, because your X and these are your independent and the dependent variable. So using random oversampler to balance our given target variable. There are many other methods of sampling. Please read them and try and understand how they kind of function on each other side if you've never really tried them. Then the random state is just to ensure it's kind of that evenness. It's a random seed. And then we have sampling strategy, not a majority. Then we pass in the X, the Y, then we fit this on there to our X and Y just to do that sampling. Then we go ahead and split our data set. So our X over sampling, so you split your data set into train and test, where you have your training aspect and then the testing aspect. So you train your model and then you test it with the testing data. Then we have the X over, so this is what we have as our X variables now being passed on here without the Y aspect, because this is what we'll use to model. Then the next part is we do get to now start creating our modeling functions. You can do this off the bat by calling the functions or the libraries immediately, or you do that or you create a function like I did. So you create a function that outputs the model's performance. I think if you do understand Python, then this is basically a function, then the function name, what it's supposed, the variables it's supposed to intake or digest, and then what it's supposed to do and what it's supposed to return. So a data frame to visualize the results of that. The first item we'll use is the decision tree classifier. So decision tree classifier basically works on decision trees and kind of calculates where to classify it by creating or generating decision trees, right? So each decision tree will be able to kind of until the very end, where it classifies if someone has diabetes or not, which is our target. So our decision tree classifier gets stored in here. So this is basically creating an instance of that. And then our random state, which is 42, which is a random seed. Then the decision tree, we fit it using the X train and the Y train, which we split against this part right here, if you can remember. Then we get to predict, pass in your X test, so that we get to see how it will predict using the test value. So after you train it, the next thing is testing it. Similarly, after we train you right now, then the testing, after you've been trained, attended your classes, the next thing you do is an examination. So similarly, that's how we get to train our models. Then the next aspect on here is we evaluate the performance. Remember this function that we created up here. That's what we get to call, and this is what it displays for us, just a beautiful display on the accuracy, the F1 score. So the F1 score is a harmonic mean of the precision and the recall, and then the AUC. The AUC is always against 1, so that's the area under the curve. Performance is always against 1 to tell you how your model performs in terms of distinguishing between the positive and the negative classes. Then the precision and the recall tells you how it's performing against rating the positive class. And then the F1 score is very good and nice when you're working with an imbalanced data set. So if we had probably maybe a 60, maybe a 50 against a 55, the F1 score would have come in handy, because it manages or is the harmonic mean of precision and the recall aspect. And that's basically the report of how our decision tree model has performed. And then we also have the random classifier, which we could also use. So these are just some of the given items. We do have some of the parameters of the random classifier, the N estimates, that's that. Then the maximum depth, that's that. For this case, I tried to kind of do a hyperparameter tuning just to compare if hyperparameter tuning using the grid search, using the grid search to find us the best hyperparameters, and it found that based on these two hyperparameters, the best was 20 and 200. Then you get to fit using the best estimator and getting to see how this actually gets to perform. The accuracy is 87, the F1 score is 87%, our AUC is 87, our recall is that, and the balanced accuracy is that. So unlike this, this is how it performed. So this performed better in terms of all aspects, actually, positive and negative classes are being predicted over. And then checking how this, so the random classifier calling it on its own without having any parameters. So remember, for here, we specified 2 parameters, that's the n estimators and the maximum depth. So just calling it on its own by default, creating an instance of this to see how it performs without doing any hyperparameter tuning. And this is kind of how it got to perform. So the precision, the recall, and the F1 score. So we can see the recall is a bit low when it comes to the non-diabetic aspects, but the diabetic aspect kind of performs a bit better. So again, recall checks your positive classes, then this combines both positive and precision. And then checking the feature importance, just to see out of this how our models, how our models found the features, right? So which features did they find most important when it came to this? And this is the rating out of 1. So high blood pressure, high cholesterol being the top, BMI, smoking, stroke, heart disease falling up, and then the least would be the aspect that fall below here. So again, this is rated against 1. And then the feature importance is a function that lies or is present with both random forest classifiers and decision tree classifiers. So it's an inbuilt function. Then we get to see how a random forest classifier, again, this is how it performed without any hyperparameters tuning, with an accuracy of that aspect. And then also our XGBoost classifier. So this is kind of how it got to perform with this given parameters. This is the performance of the XGBoost classifier and how it got to bring that up. So sampling or combining all the performances with the accuracy, F1 score, precision, recall, the area under the curve for decision tree oversampling, and the XGBoost, the random forest with no hyperparameters, and the random forest with hyperparameters. This is basically the performance of how it got to do. So the conclusion is that the features that correlated with the target, this one's still the model with the best performance is the random forest model with random oversampling, which we did initially without any hyperparameter tuning. So our best performance was 90% accuracy with a recall of 95 for the diabetic class percent. And then the confusion matrix for this is how you basically get to plot your confusion matrix, just to see how many fell into the false positive and the false negative classes, and seeing how much was lost or was not classified correctly. That's for the random forest, and for the decision tree to plot that, this is what it missed. So this one and this one. So what's in purple, that's what it missed. This is the false positive class and the false negative classes. So that's the actual number of what was missed in terms of prediction with our given models. So that's basically it in terms of the prediction aspect and creating and performing the EDA, some bit of cleaning, and how you get to look at important features and how to kind of analyze that basically. And hopefully you've picked 1 or 2 items that you can take into the Datathon item. Yeah, that's it.
Thank you very much, Diana and Millicent, for sharing your expertise with us today through your workshop, Empowering Healthcare with Machine Learning, hands-on approach. So one of the items that we're going to do is we typically are going to look at questions, but because of timing, we're going to actually share the questions with you so you can answer them in as much depth as you would like after the session. But once again, I would say, please in the chat, show your appreciation for Millicent and Diana for their wonderful workshop. It was very informative and many people are looking forward to being able to look at the code and execute the code in the notebook. So just to point out, so Millicent and Diana will answer your questions if your questions are hopefully in that Q&A panel, and they'll answer the questions via email. The WIDS team will share these questions with all of you who attended today, plus any additional resources. So that will definitely take place. Another item, reminder, is this session was recorded, so that will be shared in the next week. And just to highlight, we are at the conclusion of our workshop for today. So with that in mind, we want to acknowledge the WIDS Workshop Committee. Thank you so much for all of your efforts and everyone who helped organize the workshop. Once again, thank you to the instructors, Millicent and Diana. The workshop was very informative. And that's going to conclude today's Wednesday WIDS upskill workshops. So we have a few items that we'd like to highlight. So if you could, we're going to do the following. So for resources, we have a few items we would like you to explore. So on behalf of the WIDS Workshop Committee, thank you to everyone who has helped out. Please join us next week for another WIDS Upskill Workshop, where we're going to hear from Winter Duncanson and Grace Wilson, both of MathWorks, who will deliver a hands-on interactive workshop with the title MATLAB for the WIDS Datathon, predicting timely diagnosis of metastatic breast cancer. So we have that. Let us know what you thought of today's workshop. So in the chat, there should be a short attendee survey. You can help us optimize workshops in the future if you can give us that feedback, which is greatly appreciated. You can use the QR code, and we'll also post the link in the chat to get feedback on today's workshop. If you're interested in giving a workshop, we encourage you to apply to become a WIDS workshop instructor. So also in the chat, there should be a speaker application link that you can fill out to become a WIDS workshop instructor. Once again, thank you all for joining us today. We look forward to seeing you at another WIDS Wednesday Upskill workshop as you broaden your horizons with data science. Thank you so much, and we'll stay on for roughly another minute. In terms of resources, many resources should be in the chat. And Millicent and Diana, if you'd like to connect with many of the audience members, you could also consider sharing your LinkedIn links. You don't have to, it's not required, but feel free to share that if you'd like to do so. Thank you once again.